Hello, in this video we'll be talking about acids, bases, and the concept of pH. So what is an acid and what is a base? They're terms you've likely heard before, and you probably learned about this in high school if you took high school chemistry. Well, asking what an acid or a base is kind of a loaded question because there's a few different categories for how we can determine what's an acid and what's a base. However, in the first semester of Gen Chem, you'll mainly be focusing on the idea of the Arrhenius acid and the Arrhenius base, and you'll expand on the others later in the second semester. So the Arrhenius definition of an acid is a compound which produces either the H plus ion or the H3O plus ion when it's dissociated into water. And dissociated just means it's broken apart. So when the compound is broken apart in water, it'll either break apart into H plus or H3O plus. And H3O plus is also known as hydronium. So this is called the hydronium ion. H3O plus and H plus are pretty interchangeable. You'll see both of them used and they mean the same thing. However, in Gen Chem, you're generally going to be focusing on the H plus ion. If you go on to take organic chemistry, you'll see hydronium mentioned a lot more often. So, to measure the concentration of H plus in a solution, it's represented on a logarithmic scale. So, when you break apart into H plus, how much H plus is present in solution, the concentration of H plus, can be mapped on a logarithmic scale, and that's known as pH. So down here, we have the pH system up here on top. So this is the pH scale, and it runs 1 through 14, with 1 through 6 being the acidic section, and 8 through 14 being the basic section. So the lower the pH, the more acidic the solution. The higher the pH, the more basic the solution. So basicity is an increase in pH. Acidity is a decrease in pH. And similarly, the definition of an Arrhenius base is a compound which dissociates in water and produces the OH minus ion, which is known as hydroxide. So this OH minus is called hydroxide, and it's going to be produced in water for an Arrhenius base. It similarly can be mapped on a logarithmic scale to measure concentration. So the concentration of your hydroxide ion can be placed on the pOH scale, which is down here at the bottom. So the pOH scale is similar to the pH scale, but it's the opposite. So 1 through 6 on the pOH scale represents basic solutions, and 8 through 14 represent acidic solutions on the pOH scale. Please do not get these confused, because it's really easy to say, oh, if it has a pOH of 1, it must be acidic, when that's not true. A pH of 1 would be acidic, but a pOH of 1 would be basic. So they're inversely related, and that's how you can determine how something sits on the pH or the pOH scale. And they're both calculated using the same method, where you take the negative log of your concentration of your ion. For pH, it'll be H plus. For OH minus, it will be, for bases, it will be OH minus. So, acids can generally be thought of in three main broad categories. So you have your mineral acids, and an example of a mineral acid would be hydrogen and chloride bonded together, which is hydrochloric acid. So we will refer to HCl as hydrochloric acid, and it's an example of a mineral acid. Then you have your oxyacids, and our example here is nitric acid, which is HNO3. And your oxyacids are typically going to have multiple oxygens bonded to a central atom with the acidic hydrogen. That's the hydrogen that we think of as the hydrogen that breaks off. It's called the acidic hydrogen. Is going to be bonded to one of those oxygens. So you're going to have multiple oxygens, or in some cases just one oxygen. So you'll have one or more oxygens bonded to a central atom with the acidic hydrogen bonded to one of the oxygens. That's an oxyacid. And then you have your organic acids, which can also be called carboxylic acids, and they're going to be represented, for example, here we have acetic acid, which is CH3COOH, and you're going to see this sort of organic acid situation with a lot of weak acids. And like I said, they can also be called carboxylic. So we talked earlier about strong acids versus weak acids and strong bases versus weak bases. So here's a breakdown of the strong acids. And the term strong just simply refers to the fact that these acids dissociate almost 100%. That means they're going to dissociate into H plus and their respective, whatever they're bonded to, almost 100%. Which means we're going to produce almost 100% H plus ions. And luckily there's only 6 that you really need to know for Gen Chem. There's hydrochloric acid, there's hydrobromic acid, there's hydroiodic acid, there's nitric acid, there's sulfuric acid, and there is perchloric acid. So I would definitely memorize these. You will need to know that these are 6 of the strong acids. And these are the ones that you'll need to know when you think of the term strong acid. So these are the ones that are going to dissociate nearly 100%. So here's just a few examples of weak acids. There are way more than these 3, but these 3 are just some examples of weak acids. So hydrofluoric acid, HF, is a weak acid. Take note of this because I've seen students get confused that thinking that because HF looks like these 3 strong acids here, that it's also a strong acid when it's not. HF is in fact a weak acid. Now that's not to say that HF isn't harmful. It definitely is. I wouldn't go fooling with high concentrations of HF. It's still dangerous. But as far as dissociation goes, it's considered a weak acid. H3PO4, phosphoric acid, is a weak acid. And we talked about this earlier, acetic acid, CH3COOH, which is the acidic component of vinegar, is also a weak acid. And the term weak just means that these acids don't dissociate completely. So they partially dissociate. They actually exist in a state of equilibrium where they're going back and forth between their bonded form and their dissociated form. And you'll have to stay tuned because you'll talk more about these when you talk about equilibrium in the second semester. So conversely, for the bases, there are 6 strong bases that you need to be familiar with. So lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. And you'll notice there's a trend with these. So up here, these top 3 are from the group 1 metals, so lithium, sodium, and potassium. And they are forming ionic bonds with the hydroxide ion. And down here, the bottom 3 are from group 2, so calcium, strontium, and barium. And they are forming ionic bonds with the hydroxide ion. Keep in mind, because calcium, strontium, and barium all have a +2 charge, there are 2 hydroxide ions bonded to them because hydroxide has a -1 charge. So you need 2 hydroxides to balance the charge of the calcium, strontium, and barium. Of weak bases. So we have aluminum hydroxide, ammonia, and the carbonate ion. So don't be fooled. Just because this has an OH in it doesn't make it a strong base. So aluminum hydroxide is an example of a hydroxide base that's a weak base. So just because you see that OH doesn't mean it's a strong base. Ammonia is considered a weak base. You'll talk about more about that when you talk in the second semester about Bronsted-Lowry acids and bases. And polyatomic ions like carbonate can act as weak bases. So that's just sort of an overview of acids, bases, and the pH-POH scales. In the next video, we'll talk more about calculations you can do with acids and bases and how you can use those to refer to concentrations of your ions from the strong acids and from the strong bases.